So a couple of days, I sat down to write a code kata in which I have multiple slider or range input controls. And as I move them, you can see that they are kept in lockstep such that the summation of all the values is always 100. You can see I can move all of the individual ones here, and the sum across the three of them is always 100. 45 plus 45 is 90, plus 10 is 100. Now, when I sat down to write this, I thought that the interesting part of this code kata would be the actual slider itself. But what I quickly realized is that the fascinating portion of this experiment was maintaining the values across an arbitrary set of controls, meaning that the hard part was actually how do I distribute the change across a set of arbitrary number of values. So that's really where this became fascinating. It actually took me a couple of mornings to figure out. So let's take a look at what's going on under the hood. If we look at the app component, which is relatively simple, you can see I have a couple of sliders here, and they just take it's a unidirectional data flow, so it takes a value, it listens for a value change event, and then it handles that value change event in the component. That's what we'll look at in a moment. You can see I have the three values, good, fast, and cheap, the age-old problem. And what we'll see is that in these handler methods, which we have here, handle cheap, handle fast, handle good, they all do exactly the same thing, which is that they pipe the change, the new value, into this equalizer. The equalizer is the class that actually maintains that fixed summation across an arbitrary set of values, which again became the fascinating part of this code kata. The slider was actually not even very interesting, and to be clear, my slider implementation is extremely minimal and not very flexible or robust, because what I realized is that the equalizer part, that was the fun part of this code kata. So essentially, the equalizer takes a min value and a max value, right, which in our case is 0 to 100, and then takes an arbitrary set of values in an array. Now, the constraint that the equalizer places is that the sum of all of these values has to be equal to the max value, such that when we then change any of the values, it has to distribute the inverse of that change across the other values within the value collection, right? And you can see that essentially I have to reference these values by index, which is why when we look at these handlers, I'm saying, well, the cheap value is index 2, the fast value is index 1, and then the good value is index 0, and then I apply these results back to the view model for the app component. So let's take a look at the equalizer, because again, this is really the fascinating portion. So here's my equalizer. Again, it takes a min value and a max value, and then an arbitrary set of values. And you know, it's one thing to code against a very concrete problem space. It's another to code against kind of an arbitrary concept like this abstract, to code against an abstract concept like this arbitrary number of values. And you can see that it enforces the idea that the sum of all the values must equal the max value. Now, it only exposes a single public method, the set value. And again, we're doing information hiding here. We're encapsulating all of the complex logic. We're not telling the equalizer how to implement this change. We're only telling it that we want to change the value at this target index to this new value. And the way this is implemented is a kind of this round robin technique where I loop over the other indices in the value collection based on this last increment index, and I try to adjust the values where possible. So for example, let's just say, so first we attack the target index, which is the one that we know we want to change. There's some let's see, we don't want to change. And then essentially what happens is we figure out what the delta is between the old value and the new value. And then we get the absolute value of that. So we know that, you know, whether you're going up 10 or down 10, we know that the absolute value is 10. And now we need to distribute the inverse of that. So let's say we have to distribute negative 10 across the rest. We're going to continue to loop. And again, the way this works is a round robin technique. So I have this last increment index, and you can see that I'm pre-incrementing it here, and then if it goes past the ends of the value array, I'm looping back to 0. So essentially for every iteration here, I attempt to move on to the next value in the collection. I skipped the target one because that's the one that we know we changed. And then you can see that I get the current value at the given index. I try to increment it by the inverse portion of the delta. And then if that value changed, because again, not all values can change, right? So just coming back to the demo here, if cheap is already at 0, right, and I start to increase fast, I can't decrease cheap anymore, which means that the entirety of the inverse delta has to be applied to good. However, when I start to go fast in the other direction, you can see that we can start to apply that to both good and cheap in the inverse direction. So essentially what this does is it sees if it can apply it to the current index. If it does, it sets it on the current index, then it decrements that delta to distribute, and then it loops again. And again, we're incrementing the last index there. So that essentially, again, whenever I change good, it checks to see if can it apply it to fast. If so, do it. Then can I apply it to cheap? And then round and round and round until the entirety of this delta distribute has been moved to the other values in the index. And then once this is all done, I return a copy of the internal values, because I don't want to return the values themselves, because that would break encapsulation and expose these values to be mutated outside the bounds of the equalizer, which we obviously don't want to do. So again, this was like the really interesting part of this code kata to me. I thought it was about the equalizer. I'm sorry, I thought it was about the slider. The slider ended up not being very interesting because I quickly shifted focus. If you want to look at my slider quickly, it's not very flexible. Essentially, it has a track, a value, and a thumb. And when the user starts moving the thumb, I just call this start drag, which looks at the physical bounds of the track on the screen, and then takes the position of the mouse and essentially figures out, what percentage of the mouse is, what percentage of the physical space is the mouse at within the bounds of the rectangle, and then converts that to a value. I'll let you look at that on your own. It's, again, not super robust. It assumes that all the increments are integers. It assumes that the max and the min are integers, and that the steps are always 1. So, not nearly as flexible as even like the native range controls. Because again, the equalizer became the really fascinating part of this. And what we can see, again, going back to the app component, is that by driving the logic about the lockstep of the linked values into the equalizer, the app component itself becomes super simple. It's just the components, it's just the slider components, and then the handlers for the change events, which it just pipe the request into the equalizer. The equalizer does all the heavy lifting, takes care of all the logic, figures out how the set of values need to be maintained over the various deltas, and then the app component just takes those results and pipes them back into the view model. So I thought it was very interesting. Maybe there's an implementation of Equalizer that's a lot more simple, and I'm just missing the forest for the trees. If you have suggestions on how I could have made this more simple, I'm certainly all ears. But again, the set value, I don't know. This was a lot of fun to write, and I took a number of tries to get this right. I actually had a number of different approaches that I tried first and didn't feel as elegant. This one felt like it was a good combination of flexible and simple. So, pretty successful code kata in my opinion.